So, electrolysis review. Let's start off with a bit of a review of electrolysis because I think this is a good place to start off, and it's a good place to know sort of where we're at when we want to start moving into that exam study. So, I will be quite frank with everyone when I say I think electrolysis is the most difficult subject in VCE chemistry. I think NMR spectroscopy, which you may not have any idea what that means yet, NMR spectroscopy could arguably be the hardest, and for a lot of students it is. I found electrolysis harder, and I find that most students that I speak with find electrolysis the most difficult. Why is that? It's because electrolysis doesn't really have an endpoint. It feels like when you can ask a question about electrolysis, there's no breadth. There's no, I can't go that far, that's beyond the scope. Electrolysis kind of doesn't have a scope, and the way that they ask their questions or the way that they sort of encompass their questions can be really difficult. So that is something that we will briefly discuss when we'll do one really big practice question for this. So just to quickly point, electrolysis, really importantly, you should know all this stuff by now, but it involves the supply of an electrical energy, and essentially what happens is you do the opposite to a galvanic cell. You get that chemical energy going to electrical energy in a galvanic cell, but this time we're getting electrical energy going into chemical energy. So it's this coming backwards in an electrolytic cell. Now, what's really important is that a secondary cell encompasses all of this. So if you have a secondary cell, so if I put a 2 with an end, so if I say I've got a secondary cell, I have both a galvanic component and an electrolytic component. That is really important. It's really important to understand that a secondary cell has both chemical or both a galvanic component and a electrolytic component. Why is that important? There was a question, I think 2017 or 2018. One of the 2 years there was a question on the exam, and the question on the exam literally read, a secondary cell and a primary cell have both of what? And the answer to that, and it was a multiple choice question, the answer to that was a galvanic component or a galvanic cell. And I believe it was answered super poorly. It was like guessed, pretty much. It was like a 25-25-25 split. So really important that you understand that your galvanic and electrolytic components are part of both a secondary and a primary. Well, your secondary has both, sorry. Your primary has just a galvanic component. So features of electrolytic cell: anode stays with oxidation, the cathode stays with reduction, or reduction occurs at the cathode and oxidation occurs at the anode. The electrons still flow anode to cathode. None of this changes. This is all the same. All of that is the same. None of that has changed. What has changed is that the anode is now positive and the cathode is now negative. So if you sort of thought of things as, happy cat, or if you thought of things as sort of, what's the saying? An oil rig cat. So an oil rig cat stays the same. But if you sort of thought of things as happy cat and then the anode's the opposite, well, you need to think about it the other way. The cat is now angry. When we talk about electrolysis, if you're electrocuting your cat, it's not going to be happy. It's going to be angry. So therefore, the cathode is now negative. It's sort of a silly way of thinking about it, but it works. Now, what species are involved? We think top right, bottom left. Now, but what's really important about this is we still, and it's really important to remember this, we still utilize the strongest oxidant and the strongest reductant. Really important. So we are still using the strongest oxidant, which I find on the left, but it's the highest up on the left. And then I use my strongest reductant, which I find lowest on the right. But now, that highest on the left and that lowest on the right, I know this looks opposite in my video. I should be doing it that way because that looks the opposite in the video. The video's flipped. Now I'm interested. My left. Left was oxidant. Now, because of left and rights, God, I'm one of those people who has to put them up. Because of the left and right, so the left one here, because your left one here is highest, but it's actually going to end up lower than your reductant, which is on your right, and should be your lower, but it ends up higher. You get this, top left, bottom right, and top right, bottom left. I've got my left and rights are out the door. But that's what you get. And you end up with what is non-spontaneous chemical reaction. And this is a good way of describing it. This is now proper because you can see my left and rights. So as you can see, these are all, remember that in the electrochemical series, now, I do apologize, this is the old electrochemical series, and for some reason this has been cut off. I don't know why that's been cut off. I do apologize, that should not have been cut off. But nonetheless, in the electrochemical series, we understand that, and this is the old electrochemical series, it's exactly the same, they just removed gold and added a couple of things, but this doesn't affect this question. The electrochemical series, as you can see here, what's really important about electrochemical series is that you have this, these half equations, and all of them going to the right are reduction half equations. Why? Because the electrons are gained. Reduction involves gain. So all these are reduction. So this side is all oxidants, and this side is all reductants. And the strongest oxidants are to the top, and the strongest reductants are to the bottom. So, as you can see here, if I had copper 2 plus and I had zinc solid, I'm going to get a spontaneous reaction. So it's top, left, bottom, right. But if I had magnesium 2 plus and zinc, and I didn't have this here, this needs to occur non-spontaneously. I need to do electrolysis for this. For some reason, this is all being cut off, which is woeful. So give me 1 second. I am going to fix that up. Discard. You can have that screen while I fix this up. Oh no, I can't fix that up. Let's go here. Why did that do that? Let's bring that back. There we go. That looks better, doesn't it? All right, we're back. Hopefully that's better. Lovely, we're back. So, pushing through that, as you can see, so in this example, we discussed that if magnesium 2 plus and zinc solid were placed in the cell setting, no reaction would occur. We're comfortable with this concept, and that's a really important concept to be comfortable with. Now, what if in this scenario, you were given our electrolytic cell are not separate? If we place magnesium 2 plus and zinc in together, nothing will occur. And that's really important to understand as well. Because they won't occur spontaneously, we can put them in the same container. But once we begin to run it, magnesium solid and zinc 2 plus will form, which will lead to a direct back reaction. And that's really important. With electrolysis, you can have things in the same container, and that's okay, because there's not going to be a spontaneous reaction between these two things if I put them in the same container. But once I start to run it, what am I forming? Well, if I use a different color, let's grab the color out, which is green. Once I start running it, I form this and I form this. This looks spontaneous. So it's really important you have ways to separate things in electrolysis. And I don't believe we're going to discuss it in super detail today, but it's really important that in electrolysis, you discuss these things and you say, hey, in actual fact, I need this to occur sort of with an ability to remove the product. So if the magnesium solid forming is pulled out, that's another way that I can do it. Realistically, I'm going to have to get rid of the zinc 2 plus. Somehow I'm going to have to get rid of the zinc 2 plus whenever I do it. Maybe I have a product in there that allows it to bind and remove the zinc 2 plus. Nonetheless, there are strategies to get around this, as you can see there. So let's now consider all of these products. So let's just say that we have a mixture of all of these things in our, container. And once again, I do have the old electrochemical series. This is the new one, by the way. You can see here. There's very, very little changes. They've removed gold and they've added these three. So very little changes. There's not a lot. As you can see, there was gold up here. They got rid of that. Very, very minimal changes. What would be oxidized and what would be reduced? Well, let's utilize electrochemical series. You need to start highlighting what we've got. So if you highlight what we've got all of these things on the left and all of these on the right. Now, remember what I said before, that the strongest reductants are on the right, so R and R, and they're at the bottom. The strongest oxidants are on the left, and they're at the top. So reductants on the right, oxidants on the left. If we work off that theory, the copper, the the Cl2, the Cl minus and the O2 can be oxidized because they're both on the right. But which of these two is the most susceptible to being oxidized? Well, that's going to be the water, because the water is the strongest reductant and therefore it's going to be oxidized into O2. On the flip side, all of these things can be reduced because they're on the left, but the Cu2 plus is the strongest oxidant, so it will be reduced. So let's now do a practice question that bases itself off this sort of content. So in this scenario here, you've been given an aqueous solution of mixture of Ki, and you've been given a solution of Ca2 plus Br minus. So they're essentially the ions that are involved in that. It was electrolyzed using unreactive electrodes. What will occur at the anode? So start to think about, what is at the anode? So the anode is oxidation. What can go through oxidation here? So I need reductants that can go through oxidation. So I need my electrochemical series. So if I'm looking at this scenario here, I've got K plus I minus. So I need to look for these things. So K plus is on the left side. It can't go through oxidation. I'm fine with that. I minus can. It's up here. It can go through. It can go through oxidation. And then what else have I got? I've got Ca2 plus and I've got Br minus. Br minus can also go through it. And I can also have Ca2 plus, which I believe will be on the left side. Oh, it's on the left side. So these two cannot go through oxidation. These two can. So this and this. Which of these is the strongest reductant? It's this one here. This is the strongest reductant, therefore it's going to go through oxidation. Therefore my answer here is going to be D. As you can see there, the answer is up on the screen. The answer here is D. So really important that that's how you sort of approach these questions. Now, what's really important in this question is something that I sort of didn't discuss. What about the water? These are aqueous. So what about the water? So in this question here, it's really important you identify that there is water available. So I would need to highlight my waters. There is one here and there is one here. They are the two waters I would need to highlight. When I look at this, the water is actually the strongest oxidant. So if this was asking about the cathode, I would have been talking about water. But in this case here, I'm not. So I'm talking about this side, and this water doesn't count, by the way, because there's oxygen gas with it. This is the water we're looking at. There's more water up here, but they've all got other things with it, so you wouldn't count it. There's a water all the way up here, but this one's much stronger. So I'd be working with this water. The I is still below it. The answer is still D, but it's important to understand that. Why? Because of this scenario here. If I talk about NaCl where I've heated it up and I've made it molten, it's now a liquid and it's super duper strong. When I talk about this, it's really important to understand that I no longer have water involved. I've removed water from my scenario. So my strongest oxidant has to be Na+, my strongest reductant has to be Cl-. But if I have aqueous and I have water involved, I now have these two features. And really important, if I try and do electrolysis to this, it's going to do nothing. It's going to do nada. It'll do absolutely nothing. It'll be absolutely useless. So therefore, in this case, I need to sort of consider that in these scenarios, I need to sometimes do molten. And that's something you will have discussed. As you can see, water is preferentially oxidized and reduced. And then the last part of electrolysis that I want to talk about, I'm not going to talk about secondary cells, is Faraday's laws and being comfortable with Faraday's laws. So Faraday's laws came up as part of redox in Area Study 1. It also is mainly part of electrolysis. Why? Because in electrolysis, we apply electricity. We can count, or measure is probably a better way, we can measure the voltage and the amps or the current and the time, and therefore we can go from current and time all the way through to charge, through to our moles of electrons, and then use our stoichiometry. So really important, remember that Faraday's has two laws, and the first law implies that the mass of metal is proportionate to the charge. So how do we determine charge? Really important you remember this formula. You can find this formula in your study, in your data booklet. As you can see, it's right there. But it's also really important to understand that you should know this really off by heart. The data booklet doesn't give you the units. You need to know the units. But again, how does this relate to mass? So we determine the moles of electrons by going moles of electrons equals Q divided by F. Again, super important stuff. You need to remember this. Like, that is like a must. Yes, you will find that in here, but nonetheless, you need to know it. It's just something you need to know off the top of your head. You can't be stuffing around in an exam trying to remember that and find it in your book. So utilizing the electrochemical series, we can then use stoichiometry to determine the moles of the metal and then determine the mass. So if you had this here, use stoichiometry to determine the moles of Ni solid, and then mass via M equals N, so moles times your molar mass. So what's really important about this, just so you can understand, is that you've got to use ratios here. So if I'm trying to find this and I have moles of electrons, I have a 2-to-1 ratio of moles of electrons to moles of electrons to moles of Ni solid. So when I have that 2-to-1 ratio, it's really important to understand that in this 2-to-1 ratio, if I have 4 moles of electrons, I'm going to have 2 moles of nickel. So you do need to apply that. And it's super important that you get used to applying those ratios and you work with those ratios all the time. And then you can think about the pathway. The pathway goes forward and backwards. Once you do enough practice exams and practice papers, you'll find that this comes up a lot, and it always goes forward and backwards. And so it's really important to understand how to work with it going forward and backwards. So really important you spend that time going through and going, hey, I need to go forwards. I do need to also go backwards. So go forward and backwards. All right, so this is what I wanted to talk about. So this has been adapted from a VCAR paper. We have gone through and done it ourselves. I've given you the new data booklet as well, the new electrochemical series. I want to update on this one. Didn't update on the other one for some reason. I want you to have a go at this question. We are going to go through each of the parts. So there's this part, and then there is part 2, which we will discuss. So part 2 has, I think it's got like C part 1 and part 2. I want you all to pause and have a go at this. It's really important you start doing this and write down what you would write in a saccharine exam. I don't want you to write down, like 2. I want you to go like 2 volts is produced by this, whatever it is. Please have a go at this. I'll give you some time. 3, 2, 1, pause. And hopefully you had a go at that question. So let's start to talk about this question. Now, if you pause and then you come back and you're just confused, I will discuss how I'm going to approach this question. Then you can have another opportunity to pause. If you've done the question, you just follow all the way through. So a student carries out, in this scenario, the electrolysis of 1 molar solution of sodium chloride using graphite electrodes. So a couple of things from that. Graphite electrodes, these are inert. So these are not going to do anything to affect what's going on, but this will. So I have sodium chloride. I have sodium, and really important, it's 1 molar. I therefore have, and it says here, aqueous, I therefore have water and water. So I have these 4 things. And then it says, write an equation that would occur at the, I write a half equation that would occur at the cathode. And then it says 2 different gases are produced at the anode. Write equation for the 2 half equations that result in the formation of these 2 gases. So I've got equation for the half reaction that produces gas 1, equation for the half reaction that produces gas 2. So I've got 2 gases producing at the anode. And as it says here, I've got write an equation for the half equation that is the cathode. So bit of a confusing question because it's asking me about 2 half equations. And you're like, what's going on? Why do I need 2 half equations? We will discuss. So the cathode, remember the cathode is reduction, and therefore it is the oxidants. So reduction occurs, we need the oxidants, we need the strongest oxidant. Remember, the strongest oxidant is on the left, and lo and behold, we have water. So I would be literally grabbing this and writing this here. So I wouldn't be writing anything else, I'd just be writing this equation as it is. And as you can see from this, if I go to here, that's literally what I have done. So I have literally grabbed, that's a 2 by the way, I have literally grabbed this and written this down here. So as it says, we're electrolyzing NaCl with the strongest oxidant gets reduced. So really important here, is that in this scenario, the strongest oxidant is H2O. So that is my first step. Now, my second step is a little bit different. So why is my second step a little bit different? So it says here that I have two half equations occurring. You're like, oh, what's going on there? How come I have two? Now, I can distinctly tell you that the first one is going to be this, because it's very obvious that water is your strongest oxidant. Reductant. We are at the anode. We are going through oxidation. We are talking about reductants. Strongest reductant is lowest on the right in terms of my reductance. So therefore, this is going to be my strongest reductant. So my first equation I'm going to write out is equation for the half equation. I'm going to write that. I'm also going to write below it, just to be safe, I'm going to write oxygen is the gas produced. Full stop. That's all I'm going to write underneath. So my first line here would be this equation. Remember, it's flipped, so I'm going to do 2H2O liquid goes to O2 gas plus 4H plus aqueous plus 4E minus. I'm going to write on the line below it, just here, oxygen gas is produced. Now, what is our second gas? And that is where the question comes in. These two are very close to each other. So does that alter what is going to occur? And I would say that it will. So as you can see in this question, they have put that as the first one. You can put it as the second one or the first one, doesn't really matter. What do I mean by that? So this is a concept that it used to be part of our study design way back when, and it sort of got removed, and now it's coming back into phase, and they really want you to understand it. The electrochemical series is done at SLC conditions. We understand that. SLC conditions, 1 molar, what else is there? 1 molar, 25 degrees Celsius or 298 Kelvin, 100 kilopascals if you're working with a gas. Cool. Now, therefore, these things are really close. Now, if you alter the concentration, these will change. But also, there are going to be times where you're going to get some of this being produced because there's actually no water in contact. As you use up some of the water, there might be some points in time where you only have Cl- in contact with your anode. And therefore, you're going to get a little bit of Cl2. It's not a perfect world. You're not just going to get 100% O2. You're going to get a little bit of Cl2. Not a lot, but a little bit. And that's what this question wants you to recognize, that these are really close to each other, and therefore you will get a little bit of Cl2 gas. So I would put this as my second one, and I would write Cl2 gas will be produced. That is my second thing that I'm writing. Again, I want to put that in the second line. I haven't done it here, but I think it's important to have those two lines. Sort of instigates to the examiner and your sort of marker that you know what you're talking about, you're answering the question. All right, now let's move on to part C. Using the same current and electrodes, the student carries out a second electrolysis, this time of a saturated solution, approximately 6 molar. The sodium chloride instead of 1 molar solution. So we're using 6 molar instead of 1 molar. What difference, if any, would you expect at the products or expect in the products or the products formed at the cathode and the anode? So, I need to go back to your electrochemical series. It's really important here. So if I come across, it's really important you have your electrochemical series up. I really highly suggest just having your data book up on a tab or having it in front of you. And going back to your electrochemical series and going, all right, what's going to change here? So I want you to have a go at this question. 3, 2, 1, pause. And hopefully you're back. So, really important. This question is asking you to make an assumption. So therefore, you just need to justify your assumption and justify it as you would. So in this question, what's really important is remember, we had this and we had this. Now, I want to highlight something. This is negative 0.83. This is negative 2.71. This is nearly 2 volts different, which considering there's not even 6 volts difference between the top and bottom, that's pretty significant. There's a big gap between this and between this. Now, if I come here and I get these two, there is a small gap, 0.13. It's a tiny gap. Therefore, it's really important to start understanding how the electrochemical series works. The smaller the gap, the closer they are to each other in terms of their properties. The closer they are, that if you change some of the properties of SLC, you may get a flipping of the two in the chemical series. So the cathode, remember that the cathode was our H2O or Na+. These are too far away, way too far away. This is not going to overtake this just because it's got a lot more of it. Just because there's a lot more of it isn't going to make it stronger. It's too far away. So you know what I'm going to write here? No difference. I'm still going to have H2 gas / OH ions produced. Full stop. So by saying that there's no difference, I'm also really importantly telling the examiner that I'm still going to get the same thing produced. And it's really important that I need to say what I'm being produced. But at my anode, I'm going to get a difference. I'm going to say Cl2 gas produced with little to no HO2. Now, do I need to explain this? I think it looks good if you explain it. Yes, it's a 1 mark question, but I think it looks good if you explain it. And just say that according to the electrochemical series which occurs at SLC, Cl minus and 2H2 liquid are quite close to each other and have a minimal electropotential difference. Therefore, by increasing the concentration of the Cl minus, I will find that the Cl minus will likely become a stronger reductant, and therefore I will get more Cl2 gas produced. Full stop. Writing something like that just justifies to the examiner that you know what's going on. You are switched on. You know what you're talking about. You are going to definitely sit in their good books and get a better mark. So really important, always try and explain what you're doing. Sometimes you don't need to go over the top, but there are times where it's good to explain. Like in this first part, there's no need to explain, but the second part, there probably is. So that's just my point there. So